This is Markus Gastreich speaking, and I think we are ready to go. So, before we really get started with the science, I would like to remind you of a few things, namely that we actually have a GoToMeeting as a control element for me to show you things, but also there is a chat box in the lower right of your controls, and I have a very friendly helping hand with me, who is Christian Lemon. He is sitting in front of his computer and can take care of things that drop into the chat box, and so just feel free to use that. I have already muted you here in the GoToMeeting controls, so in case you would like to say something, just raise your hand in the chat box and we can unmute you to avoid any feedback when unmuting everybody. And actually we are recording this webinar as the other webinars before, so just sit back, relax, and enjoy this flight. Okay, so also in case any audio or video problems should occur, just let us know through the chat box so we can hopefully fix that. But well, I'm actually hoping that this does not occur at all. So this is, as you may be aware, part 2 of a sequel that we pitch to beginners, to people at the beginning of their career, maybe to interested medicinal chemists who like to get into computing a little bit more, and so on. So I pitched this overall a little bit more to be to have a lecture character instead of showcasing all various capabilities and features of the software. So here's the grand overview for the next hour. I would like to get you acquainted with the similarity principle in ligand-based drug design. Then we'll navigate into the 3D methods, what's available there, what is it at all. Point 3 should be 2D or even 0D, zero-dimensional methods for ligand-based design. Chemical spaces and searching them is a very popular topic now, arising even more strongly, especially since there is techniques to navigate and search these rapidly now. And if there is remaining time, we can hopefully also talk a little bit about automation and integration of all these pieces of software here. Okay, let's start with similarity and the similarity principle. So the central design paradigm in ligand-based drug design is the assumption that similar molecules should have similar behavior. Now, of course, the question is, what is actually similarity? What is similar? When is a compound similar to another compound? Well, mostly something like pharmacophores are assumed, at least in the 3D world, when it comes to molecular similarity, which means some kind of a three-dimensional arrangement of charges, functional groups, certain distributions of electrons, and so on and so forth. Also physical-chemical properties can come into play here. On the other hand, the similarity principle up here certainly can fail, and two of the probably most prominent failure reasons is when, for example, a binding mode changes, which means ligand number 1 binds in cavity A, and ligand number 2, which is even similar to ligand number 1, binds to another cavity. Then, of course, this paradigm does not apply anymore, and we lose the ground on which we have been standing. The second thing where this assumption often fails is for something that we call activity cliffs. Usually this translates into the fact that the descriptor that we use is insufficient, which means that the way how we describe a molecule is not really apt for the situation of an activity cliff. So what is this activity cliff? Actually, I stole this from Matthias Raray, professor in Hamburg and good friend and partner of the company, and he himself stole this from Majora, and maybe Majora stole it from another one, and in the end we all stole it from nature. So probably this is some kind of the Tuscany hills here, and this looks like somewhere in the US. So what you see is energetic landscapes can differ quite a lot. So if we take a look at these molecules here, we see the 6-membered cycle here, which differs from this position to this position to this position. So here, seen from this atom here, for example, in the 2 position, we have a nitrogen. In this molecule, this 2 position does not have a nitrogen. Here we have, in the 4 position, lost our nitrogen, which was there before. But funny enough, the affinities can quite drastically change. So for example, in the case of the root compound, we have a 70 nanomolar inhibitory power, which is quite a lot already, which can even halven for this molecule. But you completely lose affinity once you do not have a nitrogen there anymore, which means like small change in a molecule, but drastic change in affinity. And this is what we call an activity cliff. So small changes in atomic arrangement, etc., but drastic changes in affinity. So one example, which is probably one of the most prominent examples when it comes to molecular similarity in textbooks, etc., is the example of methotrexate and dihydrofolate and its corresponding protein inhibition, which is DHFR, dihydrofolate reductase. So if you take a look up here, we can see that especially on the left-hand side, these 2 molecules look still similar, somewhat, at least to a chemist's eye, but we see the pronounced difference here with this amide functionality, here having a carbonyl oxygen, whereas we have an amine group up here in the MTX. So overall, these 2 molecules look relatively similar by whatever we now have a feeling for in terms of similarity as chemists, and indeed, both inhibit the DHFR binding pocket, and they do inhibit the same protein at within the same cavity actually. So what are common descriptors then to actually capture this in a more quantitative way compared to just looking at it from our chemistry training that we have? Well, the computer can of course easily comprehend macroscopic properties such as molecular weight or a log P that we calculate for every molecule. But certainly also on a more fine-grained scale, we have the so-called 3D descriptors, which usually describe a spatial arrangement of functional groups in 3D space. Here, for example, we have something like pharmacophore fingerprints. There are all sorts of distance matrices. For example, we store in the computer every atom distance that we have, or for example certain distance intervals. So there are various flavors of these distance matrix based descriptors here. Also there are fields, for example steric fields, electrostatic fields, certain property bound fields that we can train the computer to work with, and so on and so forth. On the 2D descriptor side, this means where we neglect 3D information as an explicit part of an information, we have loads of molecular graph or connectivity-based descriptors. So, for example, topological indices such as the number of ring closures in one molecule, certain bond distances in terms of a graph distance, which means like, for example, 2 bonds in between 2 atoms, 3 bonds, 4 bonds, and so on and so forth. Or certain structural fingerprints which encode ones and zeros for occurrence or the missing of certain functional groups or elements, and so on and so forth. And various flavors of different molecular graphs, which we'll talk about in the course of this webinar. So let's first focus on the 3D approaches. So coming back to our initial example, here we have a 3-dimensional display of MTX and DHF. And you can already guess what's in between here. So in this case here, in the MTX case on the left-hand side, we see something which looks pretty red up here and bluish whitish down here, whereas this compound here looks pretty red up down here and pretty bluish white up here. And indeed, if you overlay those two onto each other, we can see why they are similar. So actually, this is one descriptor here. We can color it by lipophilicity, hydrophilicity, or even just by elements, and then get an idea of what's actually happening. So the challenge for ligand-based drug design in 3D is usually that we would like to find active molecules, but often the protein information is simply not there, or for whatever reason it's not used at this specific point here. The rationale to actually fight against this challenge, solve this problem, is the similarity principle, which means the assumption that 2 molecules which look similar should also behave similar. And the approach, I mentioned this already briefly on the slide before, is that we typically superimpose molecules to known actives, so that the properties align. And these properties then can, again, be those properties that we referred to previously in the discussion on the descriptors. So, for example, certain volume overlaps, H-bond functions should map, hydrophobic functions should map, electrostatics should be roughly similar when we overlay things, etc., etc. These are things that are being used. Then again, sometimes a closer look should be very helpful. Actually, I took this from what we call the Red Bible. This is a brilliant book which had been available for a long time in German only by Hans-Joachim Böhm and Kubini and others. It's called Wirkstoffdesign, appeared in 2002 already. And I think that Gerhard Klebe has published a remake, a redo, a much extended new book, which has also been translated into English, or which was even written in English. I haven't seen it myself yet, but I think it's out. So let's take a look at this example here again. So we have these two molecules on the left-hand side, looking at the annealed ring system here on the right-hand side, the purine right system on the right-hand side here. And if we overlay those two in a naive way, we would see that the amine functions here in the southwest will just align, and we would have this nitrogen here aligned there, and so on and so forth. So if we actually do this, let's take a look what happens with the donors and acceptors here. So an acceptor is depicted in red and a donor is depicted in green. And if we now just abstract from the actual molecule here, and we just take a look at how the arrows align or do not align, then we have this scenario down here. So we have two acceptor functionalities here at the carbonyl function, like here. We have one acceptor here for the nitrogen, and so on and so forth. What you see is you have green, red, green, green, green. So this red is missing. We have red, red up here. These two reds are missing, and we have one red, which is essentially okayish, but by far not really perfect. At the south end here of the molecules, we have green, green, red, and we have green, red, green. So it's somewhat of an alignment, but it's relatively bad compared to the situation that these two both inhibit DHFR. So if we take a closer look, then we'll recognize that that it's all about a torsion around this bond here. So we have the connection between the aliphatic moiety, the aliphatic linker moiety in the central part of the molecule, and the bicyclic system. So if we actually rotate the right molecule around this bond, what you see is that these patterns now will align much better. So we have green, red, green now compared to green, red, green. We have red, northeast, green, northeast, which is missing there. But we have an acceptor here, we have an acceptor there, 1, 2 here, aligning the two greens here to the two greens. So overall, looking at this situation here compared to the situation above, we have a much better alignment. And actually, it could be confirmed that this is actually the correct alignment that one should do. So the take-home message is, it is important to take a closer look, and just taking 2D or connectivity into account can sometimes not be enough. So sometimes it's just really helpful to also take a look at conformationally related overlays or alignments, and protonation issues, tautomer issues, and so on and so forth. So the situation is sometimes a little bit more complicated than one initially assumes. Alignment, I skipped this a little bit too fast. Alignment is an optimization problem. We should just have this clear. And this means that all various algorithms for optimization of things are actually used, and these differ from method to method. But the principal idea is that an alignment tries to overlay, to put one compound over the other. So it's an overlay of one compound over another one, or multiple ones. These algorithms can usually essentially be divided into two parts, or into two categories. One category works with fixed conformations. So typically you have preformed conformations of the ligands that you would like to align with. One prominent example for programs of this type is ROX from OpenEye. Other algorithms keep the ligands that are aligned flexible. So we essentially build up those conformations while we overlay. For example, this is done in FlexS from BioSolveIT, from ourselves. And certainly there are always associated problems, etc., etc. One could be that the conformations are simply unknown, which is usually the case if we mine from larger databases, which means that we need some means of actually generating these conformations either preformed, as here, or along the way. Binding mode differences, we had this before. These will bring our central design paradigm to fall, that similar ligands should behave similar. Sometimes also even groups or entire properties are unknown. There are certain algorithmic issues. Perhaps the algorithm is too slow for large numbers of molecules, and so on and so forth. There is a somewhat older but still nice and grand methods overview in the Journal of Computationally Aided Molecular Design from 2000 by Christian Lemon and Tom Lengauer. So if you would like to, feel free to dive into this review. Okay, just very, very briefly, FlexS in a nutshell, what is in principle done. So you see these two molecules here, the overlaid, it's our good example of MTX and DHF again. And what we essentially try to do is we try to align the functionalities to each other. So we have donor functionalities here depicted in these white glassish umbrella cutouts here, and we would like to align the same umbrellas to the same type of the other molecule, and likewise for the acceptors here. And once this is achieved, the respective alignments are output. In principle, excuse the bad quality here, so this is taken from something very old. It has kind of a tradition inherited here, this little slide, but it's still very true. So the principal idea is that we just chop up the ligand into certain fragments. One is a base fragment, that's the base fragment because we start the alignment with it. And then all these fragments have certain interaction umbrellas here depicted in blue by plus, 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 or minus, minus, minus for acceptor and donor functionalities. And then we form certain triangles of these and try to match the triangles of the molecules to superimpose onto triangles of a template molecule down here, which is depicted in light blue. And once we have started this with the base fragment of the ligand to superimpose, we will connect this base fragment to the next fragment, to the next fragment, to the next fragment, and so on and so forth. And by rotation around the connecting bonds, we try to optimize the alignment while we go. And this can be done very, very fast today. The essential problem which remains in 3D approaches is the torsional space. So these torsions can really kill us. Let's just make a thought experiment. If we have 100 valid angles here per bond, per rotatable bond, and this is supposed to be a schematic of a molecule here, then we have with 100 possibilities already 100 times 100 times 100 possibilities, which means already 1 million points to energetically evaluate. And if we just assume 1 second per evaluation, we already arrive at 11 days just for one molecule on a standard computer. That would be way too large. So we have to do something about it. And essentially, we work on a grid here so that we don't evaluate all 100 potential positions here, but we skim this down, and we don't take all solutions along while we go. So we build this up, connect one part, take the best n solutions, discard the rest, continue, again discard the others which are not sufficiently good, and discard the next ones when they are not sufficiently good, and so on and so forth. So we kind of build up a tree which we chop off loads of not promising solutions along the way. So that was a very bit of an overview into 3D methods. And I'd like to get you acquainted with the 0D or 2D approaches here now in the next part of this webinar. In case there are any questions, again, just feel free to type them into the chat box in your GoToMeeting controls, which should usually be on the lower right side of your controls. Okay, so staying with the original molecule, just to make clear the examples, the very typical 2D descriptors, which have a big and grand tradition already, they have typically a certain bit string associated to a molecule, and the bit string is a sequence of zeros and ones. And all these positions here of a bit string, they encode the absence or the existence of certain things. For example, if I have a carboxylate function, then position 3 of my bit string will get a 1. If I have a phenyl ring, then position 3, 4, 5, 6, 7, 8, 9 gets a 1. Otherwise it gets a 0, and so on and so forth for amine functions, for certain subgraphs, for certain coexistence features, and so on and so forth. And these bit strings have one advantage: they are extremely fast to be used in computation. But they also have certain disadvantages, namely, typically you lose all information about connectivity, which means if I just encode my existence for a carboxylate group here with a 1, then I have no clue how far away maybe an amine function connected to an aromatic system is. It could be very close, it could be very far. And this is usually very important for things. On the other hand, seeing that they are very fast, they are still extensively used when it comes to extremely large numbers of molecules to be looked at. So my advice would be to take the best method for the given scenario, or even to combine methods, which we'll see later on. The typical measure here, when we combine two bit strings, is the so-called Tanimoto coefficient. And I wrote down here, homework, Google this, because for reasons of time I can't go into all details here. But essentially it's the difference between two bit strings here. So another descriptor that I would like to get you acquainted to has been developed by our friend Matthias Rarey at Hamburg University, but this was in his pre-Hamburg times, and Scott Dixon here. That's the very, very first publication. Since then we have improved and worked a lot on these feature trees, and it's actually a product available from us today. So these feature trees, these F trees, how do they work? Well, you can already guess that by the name F trees, there is a tree behind, and IT people usually love trees because then they can actually solve sub-problems independently, and they can also apply very fast algorithms here. So what happens is we abstract this entire molecule here in terms of a tree, and we see that terminal atoms actually collapse to the atoms that they are bonded to, which means the carboxylate function here essentially just results in one blob. This oxygen and this oxygen are merged into the carbon function that they are bonded to. So you see that essentially this tree here follows the shape of the 2D depiction of the molecule. That's just a drawing artifact. It's just drawn in such a way that we can actually recognize better what is what. In the computer, it doesn't really matter. The computer does not have any information about angles, etc., etc., which is good and bad. The bad news first is I lose quite a bit of information about stereochemistry and automata, para, substitution patterns, and the like. But the very good news is that the descriptor becomes fuzzy. And having a fuzzy descriptor is great for scaffold hopping. So in case you would like to find something similar but not exactly the same thing as before, which is often the case in ligand-based drug design. You have one compound and you would like to find similar ones, but you don't want to find the exactly same thing. So a certain fuzziness in the descriptor is really great, and feature trees have proven over the years many, many times to actually be very powerful in that context. So what's in these blobs? In these blobs we have information about physicochemical properties, and we count the ring closures. So for example here in this blob we have one ring closure, which means we have a 1 here, and we have a so-called interaction profile. So we take the donors, acceptors, amide functions, a certain degree of aromaticity or delocalization, and hydrophobic character, and we simply count these. Up here, for example, we have a much more pronounced character here on the acceptor side. We have a degree of delocalization. It's entitled arrow here, but it should be just delocalization. we have a somewhat smaller volume, and we do not have a ring closure here. So what do we do with these trees then? Actually, just contrasting them to the bit strings that we had before, we now have the possibility to actually take connectivity into account. So even on a basic tree, we can tell the user that this function here is far, far away from the carboxylate function, although we do not have 3D conformers anymore. So we have this topology preserved. They are very fast, so essentially below a millisecond per comparison. They are chemistry aware now, so we can tell people acceptor, donor, amide function, and so on and so forth. And the nice thing is that they will have understandable similarity as an output. I'll show you on the next slide. And they are fuzzy as mentioned. I said before the stereo information is missing and the ring collapse to one node. So we lose this information about automata para, and the feature trees as such are a command line tool, which is perhaps frightening to certain people, but never mind, there are ways around this, and I'll show you how to use them very easily in a click and go context as well. So what's similarity here in the context of feature trees really? Well, it's an alignment, but it's an alignment of trees. So seeing that we have two molecules, and I abstract these now in a schematic here as two red trees, we can now come up with a computer algorithm to actually align nodes of tree number 1 up here to tree number 2 down here. For example, like this. So let's say this node aligns to these two nodes. That's possible. These two nodes align those to those two nodes, and so on and so forth. And perhaps even this one here does not have a friend on the other side. So we might even allow nil matches or gaps or whatever you may call them. The nice thing about this is that we then get just much more than a similarity score. We get much more than 0.0, 0.5, 0.7 or so, but we get the alignment, which means that we can actually tell people why we think something is similar. We can tell them this part of your molecule aligns to this part, so it's an understandable similarity. It's a graph-based alignment, as mentioned before, so it's well below 1 millisecond per alignment. It's explainable. So how does this actually work? For example, with these two molecules here, well, it's very simple. Underneath, we have these feature trees, which reflect the molecules in terms of an abstract tree description, as we had before. And the overall similarity is essentially the normalized sum of the local similarities, which means, like, take a look on this left-hand side here, for example, we have a closed ring system which aligns to an open system here. And we can tell the people, feature trees thinks that this is 0.8 similar, these two parts here roughly. We have an amine function here, acceptor function there, and so on. We have a nil match here, and we have the alignments of the trees, so people can get a feeling for why these two molecules, which initially looked not too similar at the outset, why feature trees thinks that they are similar by 0.8. Perhaps I should mention that 0 is totally unsimilar and 1 is identity in the fuzzy feature trees view of things. And also we can use this as a start point for a very fast 3D mapping, which is sketched briefly down here. So to give you a little better feeling for what feature tree similarities mean and what I meant by chemical awareness, I took a very old paper from Darren Flower here, which is a very nice read. I can only recommend this, on the properties of bitstring-based measures of chemical similarity. He looked at a query molecule like this and compared these with the 2D unity fingerprints, so fingerprints with these bit strings that I mentioned before, and compared a bromine analog to a Clarence substituted pyridine up here, and he took something pretty flat connected to a carbon hydrogen only framework and something like a long aliphatic chain and so on. And what we can see is that these unity fingerprints, they just simply cannot get this right, simply because the encoding of certain functional groups, such as a carboxylate function or a carbonic acid here, is just yeah, in a way too exact. It should be there, should not be there for a bit string to make a 1 or to make a 0 entry here. And here we have the sulfur analog of a cardinal function. So this would be a 0 similarity in terms of the unity fingerprints. For the feature trees, though, they are much more fuzzy. So we have acceptor functionalities, and we have a certain acceptor functionality up here. We have a degree of aromaticity down here and a degree of aromaticity up there, and so on. And this is why the feature trees usually distinguish these things. And I will probably repeat this. I don't mean to say that feature trees are better in all cases, but they look at things differently. They look at they look from a different angle, and this is what makes the combination of descriptors often so very powerful. I'll have examples on those likewise. So a bit more to get you a feeling. Query for a path antagonist here, and that's a paper by Bream and Lessel. If you look at these two molecules, they look pretty dissimilar. Actually, the 2D descriptors cannot fish this hit out from 1,000 compounds. It only fishes it out at rank 729 from roughly 1,000. In feature trees, given the fuzziness of the descriptor, feature trees pick those up at rank number 5, so relatively early. And then if we visualize these in terms of their feature trees, we can rapidly understand what's going on here. So we have green, red, green, green, red, green, some brown, brown, blue, green, brown, blue, green, and so on and so forth. So the fuzziness of this descriptor gives quite a bit of power to the descriptor, really. So here you see the alignment. Then there was a GPCR application by Sanofi Aventis, which has been published a few years ago, but that was very striking. So actually, by doing a little bit of magic to the feature trees, they actually arrived at a hit rate in screens of 100% here. That was really pretty impressive, I should say. I mentioned previously that I would like to talk about searching chemical spaces likewise, and by this I would like to propose you the idea of actually exploiting the chemistry that you may have in-house or that is available. We actually wrote up a little while ago a white paper on this technology, so just feel free to also go to the white paper section here and just download the respective white papers for this technology here. So the question is, could we essentially search many compounds, many more compounds than we just usually store serially on a hard disk? But could we somehow search the compounds that we would have in principle access to, the compounds that we could in principle synthesize? So that's the big question here. How could we actually do this? So let's just compute how long would we actually need to accomplish this in a serial standard brute force fashion. Let's assume one comparison just takes 1 millisecond. If we use 1 second per evaluation, then we have, I should say 1 millisecond. We have 10, 3, 6, 9, 12, so 10 to the 13th times 1 millisecond, which we would have to divide by 60 to arrive at minutes. But first we chop off the first 3 digits to arrive from milliseconds at seconds, then minutes, hours, days. Well, overall, if I did my computation right, I am arriving at 317 years for the computation of 10 to 13th similarity computations. That essentially translates to 3 years on a full 100 CPU cluster. That's pretty long, usually prohibitively long. How much hard disk space will we actually need? Let's just assume one molecule is 25 bytes. That should be roughly the size of storage that we need for a 2D molecule to be stored. So for 10 to the 13th molecules, we would need 250 billion kilobytes. Divide by 1024 for megabytes, gigabytes, terabytes, and so on, we would arrive at 233 terabytes. That's only the input, plus the output, so we would need at least 4 times the size. So typically you tell the user this molecule aligns to that one and has this similarity. So in total, we have 931,555 terabytes, which is close to 1 petabyte. So probably you should wait with this computation until we have much, much cheaper and much bigger hard disks there. But fragments can do the trick. So what do we essentially do? The initial or the basic thought of this is that fragments can form drugs. So let me just convey the principal idea. If we have interesting fragments from whatever source, maybe from your in-house compounds, maybe from generic databases of interesting fragments, and so on and so forth, then we could identify those compounds here by our technology. For example, given a template compound and we would like to align from 10 to the 13th compounds, we would like to align the most similar ones. So let's assume we had a technology identifying these fragments here. Then our technology would also have to combine those in such a way, for example, that we have a new drug, for example, Gleevec. So how could this actually work? We would need a so-called fragment space. We would have to generate a space. And essentially there are two approaches that are being followed. On the left-hand side here we have the so-called shredding approach, which means put in your compounds which you have, which exist, and shred them into pieces and put all those fragments in here. This is a shredding procedure. We chop, for example, next to rings and next to heteroatoms, or something like this. We would need some rules to actually shred these molecules into pieces. And rules are available, and fragment spaces with this history, with this anamnesis are actually available. The other idea, which has a certain appeal to it, would be chemical reaction-based. So essentially this translates to the registering of chemical reactions, which means, for example, to arrive at a compound like this, I would need my scaffold and I would like to functionalize this scaffold somehow. So this can be described in terms of a chemical reaction, and we would have to define to the computer the core and the R groups and do certain clippings in the computer to make sure that what belongs here or what could belong here actually goes there as well. And then we would have these fragments here in there. So going back from these fragments to molecules would be the way back here on this side, which would be essentially retrosynthesis or retrosynthetic approaches. And going back here would essentially be driven by the reactions that we used to actually register those fragments and the respective rules. And how could we combine these then in the computer? Well, we, with our technology, which is pretty unique here in that power searching spaces like this, we would use, for example, our query compound in terms of a search, in terms of a feature tree, and from the fragment space we would pick out fragments one by one and try to overlay these over the original query molecule by a certain miracle, and we would combine those fragments and then arrive at a new molecule. Of course, it's not rocket science, although close to rocket science. What we use there for the specialists amongst you, it's a dynamic programming technique which is used. It's a deterministic thing, and we are guaranteed within the framework of the similarity parameters to always identify the best molecule, and it's also very fast. It's essentially the same alignment technique that the feature trees itself use, but the input is a fragment space. Again, initial publication here has been written up in 2007, and since then we have worked quite a lot on actually improving further on this technology here. So what does that mean for you more concretely? So for example, you have your in-house chemical knowledge here. You could use certain combinatorial libraries if you'd like to. There is a tool which helps to set up this fragment space without worrying about duplicates and so on and so forth. It does the bookkeeping essentially. Then this query molecule could query this space. For example, one public space that we have is the so-called knowledge space with 3, 6, 9, 10, roughly 10 to the 10th molecules in there. And then we would use this technology that I described before, which is called feature trees fragment spaces, or feature trees FS. They would do the selection and will give you the results annotated with the information from what library actually you can synthesize those molecules. That's how it would work. And has it been done? Yeah, I'm going to give you a few examples here. The first being an example conducted by Pfizer. And what you see here is the scaffold hops that you have going out from the ester here. And you can see that we scaffold hop into an ether class here on the left-hand side, or into ureas, or into amide. And the interesting thing is not really the pure scaffold hop, but the interesting thing is buried here in the line underneath. DY stands for daylight fingerprints, PP stands for pipeline pilot, ECFP4s. And what you see is that the feature tree score is relatively high, 0.9, which is close to 1. So it's a very similar molecule for a feature tree. But it's not so similar for the daylight fingerprints and for the pipeline pilot fingerprints. Again, repeating what I said before, it doesn't mean that feature trees are better than other things, but they look very differently at the world. And you see the orthogonal character of the feature tree descriptor here, where again 0.97 stand over to 0.5 or 0.3 here for the pipeline pilot ECFPs or fingerprints, 0.48, 0.29, 17, 37, and so on. So this is relatively low always, this is relatively high always, and this should be an eye-opener. So looking at the chat box, I just see a question. I'm just going to read this out loudly to all of you. Where do we get these compi-libs? Can they be downloaded, or do you have to make them yourself? Well, the answer is both is actually possible. We have something kind of off the shelf that you can start with to see whether this technology is appealing to you. But certainly, especially in an industrial context, much more music, as we would say in German, much more music is in in-house knowledge. So creating your own fragment spaces from your own scaffolds that nobody else has, of course, is much more appealing in terms of a potential patentability, etc. If you're afraid of that, of course, we can help. We've done this several times now, and this is always a learning experience for both sides. So just feel free to call in for our services, and we would be very happy to actually help. But there's also things available off the shelf if you would like to get started there. Okay, another application, and I like this one very much because it exploits so much the orthogonality of descriptors, is from Boehringer Ingelheim. So they set up something that they call BI-claim, which is their own fragment space. At the time, 2009, it was presented for the first time. They had roughly 1,500 scaffolds and 30,000 reagents, and they arrived at 3, 6, 9, 10, 11, roughly 10 to the 11th compounds, virtual products. And the typical workflow that they underwent was they took a literature query and started out with TGF-beta inhibitors here, one or multiple, I don't actually recall. I think they just started out with one. And they retrieved from their fragment space, from their BI-claim, several thousand hits. And they took these hits and showed them to a shape filter. And this is really a great idea, I think, because this is a part where feature trees are extremely fuzzy. As I mentioned before, feature trees do not know about stereochemistry. Well, shape usually is very aware of stereochemistry. So here you combine two descriptors which really talk a different language. And that's great because with this you can complement a picture to a full one. So you have a shape filter, and then they did visual inspection of a few compounds here and saw that there were known pyrazoles in there, which was really reassuring. For example, to compounds here from Lilly with a low micromolar or submicromolar affinity here, 15 nanomolar here, 22 micromolar here for this compound, for example. And in a second step, then they selected certain scaffolds, designed focused libraries around it, purchased prototypes, and did further refinement, typical classical medicinal chemistry at the very end here. And they had extremely rapid successes here. On one GPCR target, for example, they very fast identified inhibitors in the lower nanomolar region here. Proteinase, target that they were working on. They identified 2 active scaffolds that they extremely fast refined down to 10 nanomolar inhibition here. This has been published in JSIM in 2009, so feel free to read this actually. And another thing that they did later on essentially follows a very similar approach in that they again used feature tree queries here, questioned their BI claim fragment space, and did a merging of results and generating shape overlap with 3D queries here, did certain filtering, post-processing, and looked at things, and again found hit classes here for GPR 119 inhibition. That has been published in JMed Chem in very late 2012, December 2012. Okay, let me just quickly summarize at this point here on the feature tree successes. That's an interim summary here before we continue with the rest. We still have a few minutes time, that's great. So feature trees are very efficient. A millisecond comparison or faster on current hardware means 250,000 comparisons per minute can be easily done on one CPU. You have high enrichment ratios. Typically, that's what we have seen over all those years that we have experience with those. And feature trees do help with various drug design tasks in ligand-based drug design, scaffold hopping, virtual screening. And they, as you've seen before, they do, for example, have a strength in matching open chains versus ring structures, something which is usually very hard for other 2D or 0D descriptors. They are an orthogonal view at similarity. Okay, at this point perhaps for academic friends I should also mention that we are of course present in the social networks. There are certain freebies, news, etc. more on the Facebook page that we have. If you prefer LinkedIn, then just go to biosolveit.com/LinkedIn, and there is free software for academics from us on our newly created Tech Trends website. There is, for example, something which has high popularity, a co-development with Roche, which is called the torsion analyzer. So just feel free to go to this website. Also industrial customers, you'll be prompted to just drop us a note, and then we'll get back in touch with you. The academics, just download the things and feel free to actually work with them. The remaining bigger challenges to close this section here. Of course, it's still not always easy to detect subtle activity cliffs. It would be very nice to even better include existing knowledge, 3D SAR knowledge somehow, and of course fragment spaces have certain devils here and there in detail sometimes. So if we have very complicated chemistries, then sometimes this needs a little bit of manual work to fix this and get this going, but usually this can be accomplished. But you know, every house has its own reactions here and there, so we keep on learning, as mentioned before. But it's a great technology to actually use for mining from extremely large spaces. Okay, I'm happy to see that we still have a few minutes to talk about automation and integration. So the idea of pipelining tasks that occur over and over is very popular. That's highly understandable. The pros of this is, of course, that people usually save a lot of time by establishing certain workflows that have proven to actually deliver once, and then to pour this into a pipeline somehow. And often also these pipeline technologies allow for simple parallelization of things without having to do the tedious work of hand splitting data, etc. And usually also modern pipelining tools have very easy to use graphical user interfaces, drag and drop is often supported, and so on and so forth. But, and I cannot stress this enough, it is typically a black exclamation mark box exclamation mark behavior underneath. So you press a button and then some magic machine just works and puts out some output, but usually without quite a bit of work, you would not see when something goes really wrong underneath. And of course, there are system-specific control points such as certain stability issues, consistency things, price things, etc. But this is of course your own decision. The two most popular I would like to mention right away are KNIME, which is free. You can download this from knime.org, knime.org. This has been developed from by the University of Konstanz in the very south of Germany by the beautiful Lake Constance, the Bodensee as we say in German. And there is Pipeline Pilot available from Acceleris, and we do have nodes for all of these. So just feel free to whatever you have or whatever you would like to use, and just get in touch with us. So for example, the F-trees in Pipeline Pilot interface looks like this. So we have many nodes for our software, and you essentially just drag from here and drop in there. You specify the parameters, input file, output file, where is the F-trees executable. You then press the play button, and then your pipeline actually works. There is an interface available for the fellow Mo users of you from the chemical computing group. This actually supports also the fragment spaces in the Mo interface in a very easy and very clean, tidied up interface here. And there is feature trees in KNIME available, as you can see here. This again essentially works over drag and drop, specifying certain variables and so on and so forth. So peeking on the right hand side, again a question in the chat box. I'm a KNIME user. Is there a webinar on how to use BioSolveIT in KNIME? To the best of my knowledge, we had this KNIME webinar already, and just feel free to get in touch with us, and we can send you a recording on actually our KNIME notes. Yeah, would be happy to. So, not better or worse, essentially they are complementing technologies, and my take-home message would always be two orthogonal views at things can help a lot already. So if you take a look at an elephant from the front side or from the side, you will already have a pretty good impression of what a full elephant actually looks like. So capitalizing here or recapitulating here, what is actually in for me? What's the added value here if I use this technology? Well, feature trees are a very new and different idea to describe molecular entities, and you can get an idea of how to scaffold hop in a fuzzy way using feature trees, and you will get understanding why feature trees think that things are similar or dissimilar here. On the feature trees fragment spaces side, you can mine from an incredibly large number of virtual molecules. 10 to the 13s, 14s have now been done. And the computation, I didn't even mention this, runs in a few minutes time only. So you don't need days. It's really extremely fast, since we break down we utilize the combinatorial character of the problem to the max, so that we can very fast really retrieve compounds from gigantically large spaces. You would only search and find what's really likely to be synthesizable, especially if you use your own input reactions and search your own doable chemistry there. Okay, with this a little bit ahead of time to save a bit of time for more questions and feedback, etc. I would like to say thank you at this point here. As announced, you will get an email soon with your 2 months extended trial license for feature trees and associated technologies. If you have any questions, please don't hesitate, be it in this chat box on the right hand side here now, or be it later on to support@biosolveit.com. Mentioned previously, you have the possibility to, of course, stay close to us. Use either the standard classic website or subscribe to Facebook and follow us on our Facebook page, or if you prefer LinkedIn, then just go to the LinkedIn page. Okay,